Hello students, in this video lecture we are going to discuss the characteristic curves and characteristic equations for a first order general quasi-linear partial differential equation. Now let me consider the form of a first order general quasi-linear partial differential equation. Now a general quasi-linear equation of first order looks somewhat like this: AUX plus BUY is equal to C, where we are taking x and y to be independent variables, and u we are taking to be a variable which is dependent on x and y, which means that u is a function of x and y, and ux of course stands for the first order partial derivative of u with respect to x, and uy stands for the first order partial derivative of u with respect to y. Now with these things in hand, a first order quasi-linear partial differential equation, the general form of a first order quasi-linear partial differential equation for the simplest case having two independent variables is somewhat like this. Now, in my earlier videos, I have already discussed what is the geometrical interpretation of this first order quasi-linear partial differential equation. Now, let me just recall the geometrical interpretation of this first order quasi-linear partial differential equation so that I can connect the geometrical interpretation of this equation to the concept of characteristic curves and characteristic equations. Now, for the geometrical interpretation, what we do is we consider the vector ABC, where of course ABC are coming from the first order quasi-linear partial differential equation, and the vector ABC is we have seen that this is a tangent vector to the solution surface or the integral surface of this partial differential equation at the point xyu. So this basically this vector ABC, whose components are coming from the quasi-linear partial differential equation of first order, this vector is a tangent vector to the solution surface or the integral surface in the xyu space at the point xyu. This we have already done when we were discussing the geometrical interpretation of the quasi-linear partial differential equation of first order. In my earlier videos, I have already discussed this. Now, the point is coming to the characteristic curves and characteristic equations with reference to this first order quasi-linear partial differential equation. What do you mean by a characteristic curve, and what are characteristic equations for a first order quasi-linear partial differential equation? Now, if you just consider the quasi-linear equation in the simplest form: AUX plus BUY is equal to C of first order. Now, when we talk of a characteristic curve, then characteristic curve in the XYU space with reference to this equation is that curve which is such that if you draw the tangent to this curve at any point, if you draw the tangent to this curve at any point, if you draw the tangent, these are the tangents, and let me take some other color. So if you take the tangents at any point, just take the tangent to the curve at any point, then these tangents must coincide with the characteristic direction. Where what is characteristic direction? Characteristic direction is the direction of this particular vector, which is the tangent vector, which is formed from the terms which are coming from the quasi-linear equation. Now this vector, we have already seen that this vector represents the tangent vector to the solution surface of the given quasi-linear equation, and in my earlier videos I have already told that this particular vector, this determines a particular direction or a direction field, and that direction is called a characteristic direction, or it is called a characteristic direction field, or sometimes this particular direction which is determined by this vector, this is also called the Mong axis or Monge axis. Sometimes this particular word, because it's a proper noun, it can be pronounced in any way, whether you can pronounce it as Monge or Mong, or there are many pronunciations, but basically this particular vector, which is the tangent vector, this determines a particular direction, and that direction is called the characteristic direction. Now a characteristic curve, by definition, is that curve in the xyu space which is such that if you take the tangent at any point to this curve, then the tangent at any point coincides with the characteristic direction or the direction of this vector, which means that if you want to find out the equation of the characteristic curve, then you can simply use the definition of the characteristic curve. Now, if you take the equation of characteristic curve in parametric form, let's say the equation of the characteristic curve are x is equal to xt, y is equal to yt, and u is equal to ut, because characteristic curve is a curve in the xy space. So there are three variables, and let's say those three variables x, y, u are functions of a parameter t or an unknown t. So t is the parameter or t is an unknown, and the variables x, y, and u are dependent on this parameter t. So if you take the equation of the characteristic curve in parametric form, now the characteristic curve by definition is that curve which is such that the tangent to this curve at any point that must coincide with the characteristic direction or the Monge axis, which is this ABC, the vector ABC. So this means that if I take the tangent vector, the components of the tangent vector to this curve are going to be dx by dt, dy by dt, and du by dt. Now, for this to be a characteristic curve, if you have to consider a characteristic curve, then this tangent vector must coincide with the characteristic direction, which means that this vector, that the components of the direction vector must be same as the components of the tangent vector. So now comparing the component by component, if you compare first, if you equate first component with the first component, second one with the second one, and the third one with the third one, you get three ordinary differential equations of first order, and the three ordinary differential equations of first order which you get are actually this. These are the equations which you obtain. Dx by dt is equal to a, dy by dt is equal to b, and du by dt is equal to c. Now these equations which are obtained by applying the definition of characteristic curve, these equations are called characteristic equations, and this is the form of characteristic equations in terms of the parameter t. So this is the parametric form of the characteristic equations or equations of characteristics. They are also called equation of characteristics. Now you can write the characteristic equations in a non-parametric form, which means that a form in which t doesn't appear. So if I just bring this dt up and bring this a down, you can write from the first term here, from this first equation, first order equation, ordinary, these are all ordinary differential equations. These are first order ordinary differential equations. So I can just write them like this: dx by a, and this one from here b down and dt up. So this is dy by b is equal to this, from this one I get du by c, and of course this is equal to dt. So this form is again another form of the characteristic equations, but this particular form of characteristic equations is the non-parametric form of characteristic equations, because t is not appearing over here. So these are the equations of characteristics or characteristic equations. And now when you solve these characteristic equations, whether in parametric form or in non-parametric form, what you get in the end are characteristic curves. So characteristic curves are obtained by solving the, or integrating rather, the characteristic equations. Now coming to the characteristic curves. Now if you just take a look at these equations, then we will find that out of these three ordinary first order differential equations, only two will be independent. So the third will be dependent on the other two. So when you solve this system of first order ordinary differential equations, there are two solutions that you will obtain, because only two equations will be independent. So two solutions will be obtained on solving the system of first order ordinary differential equations, which means that you will get two relations involving x, y, u plus one arbitrary constant, and when you integrate these equations, and the other relation will again be a relation in x, y, u plus another arbitrary constant. So when you if you just consider these equations together, then these equations together will represent characteristic curves. So characteristic curves will be given by taking together these two relations. And as far as this particular relation is concerned, the first one, this is a relation in xyu, so it's a surface in the xyu space, and it's a surface in the xyu space involving one arbitrary constant or one unknown or one parameter. So this first equation or first relation will represent a family of surfaces, because here arbitrary constant can have any value. So this is not one surface, but this is a family of surfaces. So it is a family of surfaces in the XYU space. Now this one is also a family of surfaces in the XYU space, and when these two surfaces, this one and this one, if when they are taken together, then two surfaces when intersect each other, finally you get a curve. So when you take these two surfaces together, the characteristic curves are obtained. And basically what will be characteristic curves? Characteristic curves will be, the characteristic curves in general will be a two parameter family, because one parameter is this arbitrary constant, the other parameter is this. So the characteristic curves are going to be two parameter family of curves, two parameter family of curves in the XYU space. So in general, characteristic curves are given by a two parameter family of curves in the XYU space. And if you want to find out the slope of these characteristic curves, then the slope of these characteristic curves can be obtained by just going back to the here the non if you consider the is this one, if you consider the non-parametric form of the characteristic equations, then from the first two equations here, from the first two equations, you can just see what the value of dy by dx you can find out by cross multiplying. Dy by dx comes out to be b by a. So basically the slope of the characteristic curves, the slope of the characteristic curves comes out to be dy by dx. Dy by dx is equal to b. B is in general a function of x, y, and u, and a in general is a function of x, y, u. So this actually represents the slope of the characteristic curves. And what are characteristic curves? Characteristic curves in general are two parameter family of curves in the XYU space. Now this was the case for a quasi-linear partial differential equation AUX plus BUY is equal to C. This is the first order general quasi-linear partial differential equation. Now in case this quasi-linear partial differential equation, if this becomes a linear partial differential equation, suppose it is linear. Now if this quasi-linear partial differential equation is a linear partial differential equation, in that case the coefficient of ux, the coefficient of ux is this the coefficient of ux, the coefficient of ux, which means a, then a will be a function of x and y, which means u cannot be present. And again, if the quasi-linear equation becomes a linear equation, then coefficient of uy is b, that also cannot contain u, which means that b will be a function of x and y. And in that case, what will be dy by dx? Dy by dx will be given by bxy divided by axy. So basically this is going to be the slope of the characteristic curves. And now when you solve this, when you integrate this first order equation, what you get is a relation involving only x and y. U will not be present. So it will be a relation involving x and y, and one uh, arbitrary constant will be present. So on integrating, you will have the solution will involve x and y plus one arbitrary constant, which means actually what will be the solution geometrically? The solution will be a family. It will be a one parameter family, because one arbitrary constant is there. So it will be a one parameter family. And why family? Because arbitrary constant is present. So arbitrary constant can have any value. So this means that it is not one solution that we have obtained. We have obtained many solutions. So it is a one parameter family of curves. These are all curves in the xy plane. In fact, they are plane curves because only x and y are present. So these are one para, because x and y are the only variables which are present. U is not there. So this is a one parameter family of plane curves in the xy plane. So in general, as I said, characteristic curves in general will be a two parameter family. It will be a, in general, characteristic curves geometrically will be a two parameter family of curves in the xyu space. But if the quasi-linear equation, in case it becomes a linear equation, in that case the characteristic curves turn out to be geometrically a one parameter family of plane curves in the xy plane. And one more point which I want to stress over here is that in case a and b are constants, these a and b, in case a and b are constants, then dy by dx will be equal to b by a. where a and b are constants, and when you integrate, when you solve this, then finally you will get a relation involving x and y plus one arbitrary constant. But since a and b are constants, this relation which you obtain in the end, that will actually represent a line. So this will be actually one parameter family of lines, because one parameter is there, this one unknown, this one arbitrary constant is there. So one parameter or one unknown is there, and it will not be just one straight line, but it will be a family of straight lines. So one parameter family of straight lines, because here b by a are b and a are constant, so the integral will be a straight line involving x and y in the xy plane. So this is the geometrical interpretation of the characteristic curve. So from the characteristic equations, the characteristic curves are obtained. And as I said, characteristic curves in general is a two parameter family of curves in the XYU space. But for special cases like this one, when you have the quasi-linear equation becomes a linear equation, or when a and b are constants, for special cases, characteristic curves take a special form geometrically. So that was all about characteristic curves and characteristic equations.